look at a Wittig question. So let's first look at, let's just do this. I want to make this alkene. Let's say I want to make this alkene. Or actually, yeah, say I want to make this alkene. What would the reagents be if I'm going to use a Wittig reagent for this? I have to decide, right, what kind of carbonyl, C double bond O, and what kind of Wittig reagent am I going to use. So the way to look at this to analyze this is just to simply split the alkene down the middle. Right, split the alkene down the middle. And we can go one of two directions, right? Retrosynthetic arrows. All right, if I number this 1 and 2, right? Carbon 1 could be the carbonyl part, right? Which case that means carbon 2 is going to be on the Wittig part, right? The phosphorus part. Right, here's carbon 2, right? And go the other way around, where carbon 1 could be on the Wittig part. This would be carbon 1. And now the carbonyl part is going to be from carbon 2, and that would be this. Right? So anytime you see a double bond, there's two ways you could do it with a Wittig reaction, right? You could split it one of two ways. So the question is, which way is better? So I think we hit on this. The first hour class actually got to the clicker question. The second hour class didn't get quite to the clicker question like this, but we did talk about it. So what's the most important factor? So one way to do this is to look at the differences, right? So both of these carbonyls are what? They're both ketones or aldehydes. They're both ketones, right? So if one was an aldehyde and one was a ketone, maybe we could argue a difference in reactivity, but they're both ketones, so both equally reactive as far as the delta plus of this carbon. What else is a factor though in reacting? Sterics, right? So which one's more sterically hindered? This one is more sterically hindered, okay. So that's something to think about. Now let's look at our Wittig reagents. Right. Which one's more sterically hindered in our Wittig reagents? 2 or 1? It's actually 2. So this big tert butyl actually really is bulky, right? There's 9 hydrogens sticking out here. That really makes this bad, even worse than this. Right? So at the end of the day, the most important factor is having your Wittig reagent. The Wittig reagent must be small, right? We want the Wittig part to be small. That's the most important thing. So when you're picking reagents, whenever you pick which side to go to cut your double bond, you want to make it so your Wittig side has the less amount of stuff sterically. So the preferred reagents are actually these two instead of the top two. So if you had to choose how to do this reaction retrosynthetically, you'd want to start from this ketone and use this Wittig reagent, not the other way around. So yeah, so I'll take a step back so then I'll do the mechanism after this now. For this problem, I'll do it. I am missing a methyl. Don't lose your carbons, so you should have numbered them. Now you all learned. See, that was a point there. Did that on purpose. Yeah. Yep. Absolutely. Okay. So we're going to use those Wittig reagents. Let's draw the mechanism, right? So to do that, the first thing. So usually I just draw these as methyl, but usually these are phenols. But the phosphorus just has something else on here. Usually they're phenols. But if I draw this reagent, this Wittig reagent, remember resonance arrows, that we can draw this in different resonance forms, right? And one of these resonance forms is where the phosphorus has a plus charge because it lost electrons, right? These electrons move toward this carbon 1. And now the carbon 1 has a negative charge. Carbon 1, negative charge, right? So sometimes that's an easier way, I think, just to see how it's going to react. It doesn't have to be that well, but I think it's easier to see it with this. So now this is going to interact with this carbonyl, which has carbon 2 on it. Right? So what's going to happen is carbon 1 is going to attack. At the same time, these pi electrons are going to go after the phosphorus, and now that oxygen is going to be bonded to that phosphorus. Right? And so we're going to get so remember, phosphorus is still bonded to carbon 1, and oxygen is still bonded to carbon 2. And now I just got to fill in what else is on there. So carbon 1 had 2 methyls. And then carbon 1 had 2 methyls. Carbon 2 had the tert-butyl and a methyl. And so there you are. All right? And so at the end of the day, we know we want to break the P-C bond and the O-C bond. Phosphorus carbon, this bond right here and this bond right here, the O-C bond need to break. So let's break them. These electrons come down. These go up there. So we get the phosphorus, right, like that, double bond to the oxygen. And we get the alkene that we started out with. Carbon 1, carbon 2. Let's take a simple amide and react it with lithium, aluminum hydride. And then a lot of times in the homework, the second step, they'll say just water. The reason they say just water, because since the lithium aluminum hydride, H minus, is so much more reactive, if you reacted that with H plus, it'll literally explode. Yeah, right? So I actually have a shirt I can show you guys that has aluminum. I got aluminum hydroxide oxide on it. Now there's holes in it because of it. It's really great. It's too bad. This may be another reaction that blew up in my face once upon a time. Not blew up. Pressure built up, and there was a minor spill and explosion. It wasn't technically. Yeah, it was my fault. It was absolutely my fault. Besides the point. So that's why, right? You can just use water instead of H plus. So it's no different. It's just a place to get a proton. So if you want to write H plus, that's fine. But the book will show water instead of the homework. That it's just the same idea. You eventually get O minus with no good leaving groups. Water is going to give you a proton. That's all it's saying. So now, lithium aluminum hydride, right? We just kind of said this is a really strong source of H minus, so we could draw it. But we got to remember one thing. So we got to remember that our amide's very reactive. Is this carbon very electrophilic? No. So, right, especially in the case where, in this case, there's a bond to hydrogen that might be slightly acidic, right? Remember we saw the carboxylic acid, the OH? So an NH bond, right, is relatively acidic, right? Especially with H minus, which is really, really nucleophilic, or really basic. So that's the first thing that's going to happen, is that these electrons here are going to attack there.
So that would happen, like NH, OH?
Yes. Yep, anything. That's why water will stop the reaction, right? Water essentially stops the reaction at the end of the day, because it's an OH bonds. So then we could draw some resonance structures here, right? Because these are not equilibrium, right? Because what's the byproduct here is going to be H2 gas, which is just going to, literally you'll see bubbles come out of this. That's part of why it blew up in my face, because I didn't have a vent when I was trying to stop the reaction, right? So if you make gas and you have a closed system, guess what? Boom, right? So that's one of the things that always scares me about organic lab, is that people don't think, people take your top off. People don't realize closed systems and how that works. Okay, so resonance structure, right? Because who would rather have the negative charge, oxygen or nitrogen? So let's give oxygen the negative charge. And we kind of, hopefully maybe we know this at the end of the day. Right, so ideally, right, when you look at these, if I gave you this, you should be able to look at this right away and say, oh, that's going to give me an amine. And you'd immediately draw this. Right? So ideally, you'd see this and draw this right away. And know the product. Because then once you know the product, right, then it's just a matter of drawing the mechanism to form that product. That gives you the guide, right, that says, okay, what bonds do I need to make? What bonds do I need to break? Right? So we know we need to lose water. Or O at some point, I guess, not water. So now we have O minus. And remember, we still have AlH3 floating around, right? Well, aluminum's a metal. So that O minus is going to go after that. Negative charge on aluminum. And now remember we talked about the intramolecular part where this aluminum, right, has a negative charge again, so all these H's are little hydrides, right? Every lithium aluminum hydride has 4 H minuses, so we've used 1, now here are 3 more, and we know we need to get 2 H's here, and it's an intramolecular reaction, so the electrons can come here, go up, I went too far up, but we'll get there. Negative charge on the aluminum, and we put 1 H there, right? Everybody sees that? We also know at the end of the day, we know we're going to need to add 2 H's up here. Oh my God, what have I done? Oh my rod. That's close. Ish. Oh, here we go. Nope, don't do it. There it is. So there's the negative charge on there. That was exciting. Alright? So now the negative charge on the nitrogen. And this is where we kind of start to think about, when you see aluminum with the oxygen, it's kind of looks like an activated alcohol, maybe. You've seen oxygen bond metals before. These electrons come down, this goes there, right? You form a new pi bond between oxygen and aluminum. And you formed, oops, I don't want to use that color. You've also formed what though? An imine, right? You formed an imine. Negative charge aluminum, H. Well, imines are, right? The carbons of imines are electrophilic, right? So that comes up. Okay, doesn't want to do it. Go to another page. So that comes up. So this nitrogen has a negative charge there now. It looks like a nitrogen some days. Nope. So nitrogen has a negative charge, pretty unstable. You can imagine the next thing, right? So it's like a tetrahedral intermediate. Do you have any good leaving groups now? There's no good leaving groups, right? Left. So once you run out of chances for leaving groups, that's when the water comes in. And so because nitrogen's so unstable, negative charge is really unhappy, you'll make this amine. All right, you've added these 2 H's as well. So that's why you turn amides into amines, right? So let's do another one with esters. Ethyl acetate. And we still have to use lithium aluminum hydride because sodium borohydride is not reactive enough, right? Esters are not that good of an electrophile because of resonance, right? So we still have to use lithium aluminum hydride, H4, 2, and then probably water at the end to stop it. So same idea, a little bit different. Because here, are there any acidic H's? Are there any hydrogens bonded to O or N? No. And esters are more reactive than amides, right? So because this is so reactive, we can actually attack the carbon of the carbonyl group. So we form an O minus. We've added an H, and then we have AlH3. So tetrahedral intermediate. Are there any leaving groups? Right? The oxygen can be a leaving group, so we bring these down. And this comes out. Good. So we make an aldehyde, right? And aldehydes are actually more reactive than esters, right? So this aldehyde is not going to stick around very long with a bunch of lithium aluminum hydride around, right? So what's going to happen is some more lithium aluminum hydride. H minus is floating around. So sure enough, that will react. I'm just using another one, right? So I can give you there's more to this story, but I'm just not giving you the whole story. So just imagine there's a lot I can show you in a second, right? It's not really an excess, but there's a reason why. So then at the end, once you have a tetrahedral intermediate, right, and there's no good leaving groups now for this guy, no good leaving groups, then you want it. That's when the water comes in. Right, and you make OH minus. But you get your primary alcohol, right? You can turn esters into primary alcohols.